We were talking about the relationship in class between the distributive law and multiplying polynomials together. We also were talking about factoring, and finally we talked about division. And I made a point in class about the relationship between the multiplications and geometry. In particular, I was talking about the distributive law as it applies very simply to an expression like 2 times x plus 3. Now, multiplication really comes to us from thoughts of area and rectangles, and if you'll recall, the area of a rectangle is height times width. So mentally, what I'm thinking about when I process this problem, and I don't really think about this each time, but it's a way to make it make sense, is I think about a rectangle that's 2 units high, and its width is x plus an additional 3. And when I use that thinking, I notice that I've really got, in a sense, 2 different rectangles. One rectangle with an area of 2 times x, and the other rectangle with an area of 2 times 3, or 6. Since I'm interested in the total area of the large rectangle, I simply add together the areas of the 2 smaller rectangles, and I end up with 2x plus 6 as my total area. Now that might seem pretty trivial, and it should. Where it gets a little bit more interesting is when we start to work with rectangles or regions that have more than just 2 pieces. Now, probably at some point in your learning of algebra, you probably learned a mnemonic FOIL. And FOIL stood for first, outside, inside, last, and many students learn that without learning any reason behind it. What I'd like to do is I'd like to take a minute to talk about why FOIL really probably is not the best mnemonic to use for multiplication, because it limits you to binomials, and I'd like to extend this idea out to multiplication where the 2 factors in the multiplication have more than just 2 terms. So let's first talk about FOIL. Let's look at a simple one like x plus 2. Now this is a binomial because we have 2 terms, that is quantities added together within the parentheses, and we're going to multiply that by another binomial. Let's make it x plus 3. The thinking that I use is similar to the thinking that I used before. I'm going to think about a rectangle where one dimension of the rectangle is x plus 3, the other dimension is x plus 2. And while I normally won't draw this for this demonstration, I'll suggest here the individual rectangular areas that I'm going to be looking for. In this case, you can see 1, 2, 3, 4 different areas, and those areas are x squared, 3x, down here I get 2x, and in the bottom corner 6. Now, one point to notice, and that is that these 2, sorry about that, I just managed to shrink the screen down a little. These 2 located on the diagonal are what we call like terms. Notice that this is 2x and 3x, same exponent on the variable. They're like terms, they add together. They can be combined using our distributive law. And so our final answer to this problem becomes x squared plus 2x plus 3x, which is 5x, plus the remaining cell, which is 6. So there's FOIL. Again, we talk in FOIL about first, outer, inner, and last. And that's what each of these individual small rectangles represent, are those 4 multiplications in this case. Again, the limitations of FOIL come from the fact that FOIL is limited to a 2 by 2, a binomial times a binomial. So in a sense, if all you've memorized is the mnemonic FOIL, you're going to run into trouble when you see this problem. X minus 1, no problem, times x squared plus 2x minus 3. Now what? Well, the FOIL method, as I said, falls apart on us, but if we buy into this area idea, we can simply think of, again, a large rectangle, this time split into 3 across the top, x squared, 2x, and minus 3. Subtle point here, notice I've now, if we're thinking about the area model, I've actually got what would have to be considered a negative length. That's not important, it works out. There's an argument as to why it does, but we won't take time with that argument right now. The other dimension, x, and again a negative, -1 in this case. Notice, if I were to draw the dividing lines between the cells, there would now be 1, 2, 3, 4, 5, 6 different cells in this large rectangle. So there are a total of 6 multiplications that have to take place. X squared, x cubed, 2x squared, negative 3x. Down here we get a negative x squared, negative 2x, and a positive 3. And again, notice, as I mentioned up here, on the diagonal, from lower left to upper right, we had terms that were like terms. In this case, that happens again. Here's a pair of like terms, and here's another pair of like terms located diagonally from each other. So when I add those like terms together and write the result, I have x cubed, negative x squared plus 2x squared, so that's negative 1 plus 2, which is plus 1x squared. And then I have negative 2 minus 3 of the x's, that's negative 5x. And finally plus 3 from down in the lower right-hand corner. So this is a method that I'll use over and over for showing distributive law, or for using FOIL, or multiplying binomials, or in the broader sense, multiplying together any two polynomials. Next, we'll move to a look at factoring. And I'd like to note that I'm going to use exactly the same process here, or really I'm going to make use of the same geometric model, but in reverse this time. Let's suppose that, and we'll look at a couple of examples here, let's suppose we have the quadratic x squared minus 7x minus 18. And we're interested in finding, first of all, whether there are two binomials that multiply or have a product of this quantity, and secondly, finding out what those two binomials would be. I'm going to again think of the rectangular model. Now, if you remember from the earlier example, the quantities that fill the area of the rectangle were quantities that add up to this amount. So I know, for example, this corner, let me draw those rectangles in here again to make it a little bit more evident what I'm talking about. And again, I won't do this each time. I will draw that little angle bar at the top on each problem. In this cell must be x squared. These two cells being on the diagonal, they must be the two cells that together add up to negative 7x. And down in the lower corner must be the number negative 18. Well, as it turns out then, the big problem of factoring if you think about it from a geometric perspective, is to figure out what values need to fill in these two cells. Nothing hard about putting the x squared in here. Nothing hard about putting the negative 18 in here. But what we need to do now is we need to find two numbers that add up to negative 7 so that the product of those two numbers is going to give me, in this case, negative 18. So what I'm going to look for, and a little visual that I use for this, is I'll draw a little x, and I'll take two numbers. On the top, now this is a simple example because my lead coefficient is 1, but on the top here, I'll put the product of A and C. If you think about ax squared plus bx plus c, up on the top I'm going to put the product A times c, which in this case is 1 times negative 18, or negative 18. On the bottom, I'll just enter the value b. Now you might use another graphical approach to this. I just use it because it's convenient, and in this case the b value is negative 7. Now what's my challenge here? My challenge is to find two numbers to fill in left and right, where the product of those two numbers is negative 18 and the sum of those two numbers is negative 9. Now I know the answer to that quickly because I've done this before and I can think through this fairly quickly. But a typical way to approach this is to start to break negative 18 down into its factors. And I know I want those factors to add up to a negative number, so I'll make the larger factor the negative, larger in an absolute value sense, and the smaller factor positive. So one possible pair of factors that multiply to negative 18 are negative 18 and 1, but those two numbers add up to negative 17, so they don't fit the necessity of adding up to negative 7. Another pair of numbers would be negative 9 and 2, and lo and behold I can stop searching because the sum of negative 9 and 2 is negative 7. So the use of this was really just to find again the negative 9 and the 2, because those are going to be the two quantities, adding an x to each. Negative 9x and 2x are the two quantities that together add up to negative 7x. Now, if you think back to the original problem of the distributive law, we now, if we just look at one row of our picture here, we can ask ourselves the question, what's the greatest factor? Or what's the largest quantity that divides evenly into both x squared and 2x? And in this case, that answer is x. And this starts the factoring process because x times some quantity gives me x squared, so that other quantity must be x. X times some quantity gives me negative 9x, and so this must be negative 9. X times some other quantity must give me 2x, and so this must be 2. And I can now check my answer to see if it's reasonable by looking at the two numbers that I entered in here, the 2 and the 9, and notice that they do multiply to give negative 18. So this graphical development again leads me to the factorization of x squared, let's do this correctly, x plus 2 and x minus 9.